Today, we're on a mission to uncover something truly fascinating. We're looking at exactly how some of the most brilliant engineers in the world are literally hacking low-precision AI chips to perform rigorous, mind-bendingly complex scientific simulations. We're diving deep into the research on how AI hardware, specifically the Ascend 910 NPU series, is being forced to do things it was never, ever originally designed to do.
I really want you to think about this question for a second. Right now, practically all the cutting-edge silicon in the world is being diverted toward artificial intelligence. It is an absolute gold rush for AI compute. But where exactly does that leave traditional scientists? The physicists, the chemists, the climate modelers? As our data centers completely fill up with AI chips, traditional high-performance computing researchers are left wondering if they're getting left behind, or if they can somehow hijack these AI engines for their own scientific discovery. To understand the massive challenge here, we have to compare two drastically different computing paradigms. See, AI workloads absolutely thrive on low precision and dense, highly regular math. Think of an AI chip like a Formula One car. It is built for blinding speed on a perfectly smooth, highly predictable track. Scientific computing, on the other hand, demands extremely high precision and relies on irregular, memory-bound logic, so it's kind of like demanding that exact same Formula One car navigate treacherous off-road terrain. The math just doesn't match the machine. To make sense of this, we're going to break this massive technical puzzle down into 6 logical steps. First, the AI hardware dilemma. Second, the 3 fundamental gaps. Third, a look inside the Da Vinci architecture. Fourth, hacking precision. Fifth, taming memory. And finally, the future of high-performance computing.
Okay, let's dive right into this and set up the core problem facing the computing community today with parts 1 and 2, the AI hardware dilemma and the 3 fundamental computing gaps.
The hardware landscape is undergoing a massive, tectonic shift right now. Flagship computing systems are becoming progressively more expensive and almost entirely AI-centric. These dedicated AI chips prioritize extreme throughput for low-precision tensor operations because that's the exact kind of math neural networks love. But since this hardware is totally taking over, researchers really have no choice. They absolutely must adapt critical scientific workloads to run on hardware that was, frankly, built for a completely different job.
And to do that, they have to defeat a 3-headed enemy. These are the 3 fundamental gaps that will essentially form our mental checklist for the rest of this explainer. Number 1 is the execution mismatch. AI chips love dense math, but science is often memory-bound and chaotic. Number 2 is the precision gap. AI uses super-fast, low-precision 16-bit math, while science needs highly accurate, robust 64-bit formulations. And number 3 is the data movement gap. AI chips require explicitly managed memory transfers, while scientific apps often rely on incredibly complex, multi-level data reuse.
So what are we actually working with here? That brings us to Section 3, inside the Da Vinci architecture.
We really need to unpack the anatomy of the Ascend 910 NPU series, because it's the key to everything. At the core is the Da Vinci architecture, and there's an explicit hard split in how it computes. On one side, you have the AI cube. I want you to think of the cube as a massive sledgehammer. It's designed for incredibly dense matrix math, offering massive throughput, but it absolutely requires highly regular data tiles fed through very specific L0 and L1 buffers. On the other side, we have the AI vector unit. Think of the vector unit as a precise scalpel. It's highly flexible, handles complex logic, and talks directly to a fast, on-chip unified buffer. But here is the catch. Both of these units share a software-managed multi-tier memory hierarchy, pulling from the L2 cache and global memory. The programmer actually has to explicitly orchestrate exactly how data moves between the sledgehammer, the scalpel, and the memory.
So we have 2 very different tools sitting in the exact same toolbox. The cube gives you extreme world-class throughput, but it demands rigid, perfectly regular data tiles. If your math isn't perfectly shaped, the cube just chokes. The vector unit, on the other hand, is amazing for handling complex logic and irregular reductions, but it suffers from much, much lower peak performance. It's flexible for sure, but it isn't going to give you that blazing AI-level speed. Now, zoom out from a single chip for a second and think about how we wire these together to build a supercomputer. At the base, you have individual Ascend 910 dies. 2 of these dies are actually connected inside a single chip package using ultra-fast SIO links. Then, as you move up the hierarchy within a single node, 4 of these chips communicate via the HCCS scale-up network. And if you need to tackle massive distributed scientific workloads, you scale out across multiple nodes using an RDMA plane known as Routh. The speed of your science is entirely dependent on how cleverly you can move data through this specific, highly structured maze.
And this brilliantly illustrates exactly what happens when you run scientific math on this hardware. When we measure achieved throughput, dense matrix math, often called HGEM, running on the cube absolutely flies. It hits over 300 teraflops on the 910C. But a matrix vector operation, which is irregular and memory-bound, barely scrapes 1.5 teraflops. Why the massive difference? It comes down to what's called a roofline model. The absolute maximum compute speed of the chip is the flat roof at the top, while the memory bandwidth limit is a slanted roofline leading up to it. Dense math pushes all the way up to that flat compute roofline, but irregular science math, it crashes straight into that slanted memory roofline. The hardware is just starving for data.
Which shifts our focus to the first of our major case studies, Section 4, Hacking the Precision Gap.
Now, what's really interesting about this first strategy is how engineers force low-precision AI chips to do high-precision science for LU factorization. They realized pretty quickly they can't do everything on the NPU, so they aggressively split the task. The dense, low-precision, brute force matrix multiplication is sent straight to the Ascend NPU's cube unit, running in fast 16-bit precision. But the sensitive, rigorous math, like the triangular matrix inverse, would completely blow up in low precision. If you run that on the AI chip, your simulation just fails, so they keep that safely on the host CPU in 64-bit precision. By pipelining these operations together and hiding the communication time, they get the sheer speed of the AI chip combined with the rigorous accuracy of the CPU.
We actually see a very similar brilliant trick when dealing with singular value decomposition. The engineers push the heavy lifting data parallel phases, things like QB decomposition and the Lanczos algorithm, right onto the NPU's vector and cube units. But there's a phase called the symmetric QR algorithm that involves heavy branching logic. AI chips absolutely hate branching, so they leave that safely over on the CPU. Now, even on the NPU, running in single precision can cause rounding errors to accumulate, degrading the math. To fix this, they inject a super clever iterative orthogonalization refinement loop. Essentially, they are checking and correcting the math repeatedly on the fly to prevent the single precision AI chip from drifting into error.
And man, does this NPU-CPU splitting strategy pay off. When you look at execution time scaling as the matrix size grows, the hacked Ascend NPUs achieve an order of magnitude speedup over heavily optimized CPUs at massive matrix sizes. Furthermore, performance sensitivity data proves exactly where this hybrid trick shines. In the low-rank, data compression regime, this hacked NPU workflow outright dominates top-tier classical GPUs. It's not even close.
So, the crucial point is, sometimes you just need pure high-precision matrix math directly on the NPU, without relying on the CPU at all. How do you do that when the NPU only natively likes 16-bit math? Well, you use an incredibly clever hack called mantissa splitting. The developers literally chop a 32-bit high-precision number straight down the middle into two 16-bit halves, a high part and a low part. They feed these hacked 16-bit pieces into the AI tensor core, tricking it into doing the math natively at blisteringly high speeds, and then they carefully recombine the results back into a perfect 32-bit answer at the end.
Let's break down exactly how well this mantissa splitting hack works. When mapping relative error, if you just use native 16-bit math, the error rate is terrible. It's completely unacceptable for science. But with the mantissa splitting trick, it achieves a flat, perfectly stable, low error rate that identically matches a true 32-bit calculation. And when it comes to performance, standard vendor implementations often drop off a cliff as the problem gets bigger because of cache issues. But our hacked version stays incredibly steady, sustaining a flat 60 teraflops across massive problem sizes without crashing. It is relentlessly fast and flawlessly accurate.
Okay, it is time to move on to the final boss of scientific computing. Section 5, Taming the Data Movement and Memory Bottleneck.
Let's move to a whole new domain and see how this builds when simulating quantum circuits using a tool called PQSim. Quantum simulation is entirely memory-bound. The AI chip spends practically all its time just waiting for data to arrive. To fix this, engineers use something called gate fusion. It's a circuit-level pre-processing trick. Instead of sending one quantum operation to the NPU, waiting, and sending another, they mathematically fuse consecutive quantum gates into a single, massive composite kernel. This prevents the NPU from constantly stopping to talk to the incredibly slow global memory. But fusion isn't quite enough on its own. They have to pair it with a strategy called cache blocking. Remember that fast unified buffer we talked about in the Da Vinci architecture? The full quantum state vector is way too big to fit in there. So they slice the vector into smaller tiles. They load a specific tile of complex amplitudes directly into that ultra-fast on-chip unified buffer, and because they fused the gates earlier, they can apply multiple updates back-to-back right there on the chip. Only when they're completely finished do they write it back out to global memory. This completely slashes execution time in half and allows the Ascend NPU to consistently be top-tier classical GPUs.
But what if your science is totally chaotic? Monte Carlo simulations, for instance, are highly random and irregular, which makes an AI tensor core essentially want to cry. To run them, engineers had to completely regularize the chaos. First, they built a dual lattice configuration. Instead of sequential accept or reject logic, they buffer post-trial local energies in a second lattice. This separates the math from the decision-making. Second, they stripped out unpredictable code branches, those if-then statements that choke AI cores, and replaced them with highly regular SIMD vector masks. They're basically computing everything, but only keeping the answers they actually need. Lastly, they staged everything through that unified buffer. They literally took a chaotic workload and forced it into a highly predictable, batched vector stream.
All right, let's step back and look at the big picture of where supercomputing goes from here in Section 6, the future of HPC. The core takeaway from all of this incredible research is quite profound. Yes, AI accelerators absolutely can do high-performance science, but out-of-the-box AI chips will not solve scientific problems natively. The math simply doesn't align. To get these incredible speeds, researchers have to treat algorithmic design and hardware mapping as a joint puzzle. We have to brilliantly and sometimes ruthlessly manipulate our algorithms, splitting mantisses, fusing gates, decoupling logic, just to make them fit these rigid high-speed architectures. Which leaves us with this final, provocative thought. We are fully entering an era where AI dictates the silicon we build. As these specialized tensor chips take over every single data center on Earth, a massive question remains for the ultimate trajectory of human discovery. Moving forward, will we continue to adapt our science to fit the hardware, or will we eventually demand that the hardware adapt back to our science? Thank you so much for joining me on this deep dive. Keep questioning, keep learning, and I'll catch you on the next explainer.